Rotary encoders. You get a couple on eBay and they have a power ground, a push button shaft switch, and two data pins called clock and data, which we could also just call A and B, it doesn't really matter. What if we don't really feel like using an Arduino or a microcontroller to decipher the two output pins? These generate square waves that are offset from each other as you rotate, and depending if you're going clockwise or counterclockwise, one output is going to lead the other. And analyzing those pins, you can tell which way you've rotated and how many times. But sometimes it might be useful to just be able to use this without software on the bench. Maybe you don't have time, or you don't have a computer near you, or you can't be bothered to write the software, but if you have a few typical logic gates and flip-flops, maybe you can put this to use, at least for prototype purposes. There's several ways to do this, and I'm already thinking about a second, simpler way, but here's a more universal, maybe more complex way, but maybe somebody has an idea they can use this with. If not directly for using it on an encoder, just going through the fundamentals, getting refamiliarized with digital logic can be useful too. Here's the rotary encoder on its own, and output A and B are here. So output A is scope channel 1 on the top, output B is channel 2 blue. Going on the module names, A is clock and B is data. So I'm giving it 5 volts from a bench power supply, and I have everything hooked up. So when we go clockwise, we should see both of these A and B outputs momentarily go low in sequence. One will drop, and then the other will drop, and then the first one will rise again, and the other will rise again as it is rotated. Whichever one drops first indicates which way we're going. The way it's hooked up, if A drops first, we're going clockwise. If B drops first, we're going counterclockwise. So I'm going to go clockwise, and we should see yellow drop first. And it does. A dropped, and then shortly after, B dropped, and then A went high, and B went high after. Do it again. So this one was a slower rotation movement, so it took longer. A drops, then B, A rises, then B rises, going clockwise. If I go faster, I get a couple of those. If I go really fast, luckily I did not get any contact bounce. I do sometimes get contact bounce, but this looks relatively clean. So A keeps going low first. And then we rotate again and again. So here, when they're both high, it's idle. Then it caught another rotation and I was going clockwise. A goes low, then B, A goes high, then B goes high. We're idle again. Going counterclockwise, that was a good full screen slow move. So counterclockwise, they were both high, which is idle. Then B went low first, followed by A, and then B returned high, A returned high. Going faster, again we're idle. B keeps going low first, we go idle. B went low first, we go idle. B went low first, going counterclockwise. So using this is a clockwise rotation. What we need to do is detect basically which one went low first when they're both idle, and if it's A that went low first, it's clockwise. If B went low first, it's counterclockwise. After we've detected this, which we can do from this opening portion, somewhere around here before we go back to being idle, waiting for another rotation, it's a good idea to generate our output signals to say what we've interpreted before this goes high again. And I'm just going to detect which direction, and I'm going to have two outputs, one that I'm going to assert if I detect we are going clockwise, somewhere around here. And if I'm going counterclockwise, I'll assert the other line, dedicated line each. So by the time I'm done generating my output, the rotation is also done, and it's ready to rotate again, and I'm ready to detect it again. This is roughly how the rotary encoder works. You have two contacts in there called A and B. I will call them arbitrarily A and B like this. Then you have this disk, which is going to be tied to a common, and on the module they make that a common ground, and then they take A and B and they call them clock and data, and they have pull-up resistors on the board. So when these are not making contact, they're getting pulled high. If this is rotating clockwise, this metal conductor is going to first hit A and ground it. So now A is low, B is still being pulled high. And then as this continues moving clockwise, both A and B will be grounded as this tab moves under both. Then as it keeps rotating, A is going to no longer make contact, so A is going to be pulled high while B is still low. And when it has totally moved through, you're back to neither are making contact with common. A and B are pulled high again. So it would look something like this for clockwise. When nothing's happening, A and B are pulled high. When it starts moving clockwise, A will go low, and shortly after, B will go low. So for this time, B is high, A is low. The next state would be B is low and A is low, and when the tab moves on through, B is still low, but A is now released high, and then finally B is released high, and we're back to an idle state. A and B are high. If you move again clockwise, the same thing happens. A goes low, then B, then A goes high, and B goes high. So this sequence is guaranteed by the mechanics of this. And going counterclockwise, if this were to rotate counterclockwise, it would first ground out B, so B goes low while A is still high. And then so on, both will make contact with the tab, so both go low. Then, as this rotates on through, it'll release B, but it's still touching A. So B is released, it pulls high, while A is still low. Finally, this rotates all the way out, and A and B are no longer touching common, so A and B are both pulled high and go into a default idle state again, not moving. Normally, this would be monitored by a microcontroller, maybe with interrupts, so you get an alert when something's happening on either of these, and then you can analyze the sequence and determine which way is it rotating. But it's not always preferable or convenient to do this in software, so there's a couple of ways to do it in hardware, and one way would be to use a D flip-flop. So if you have a flip-flop with its Q bar outputs, data in, and an edge-triggered clock in, you could just choose whichever you want, A and B, and feed one to the data, one to the clock. So in this case, if A is on the clock, every time you get a rising edge of A, the data on B will make its way out to Q. So that will be right here or right here, and it acts as a latch. So in this sequence, when A goes high, it'll throw B out to Q, and B happens to be low. So Q would go low. In the counterclockwise direction, when A goes high, this will be occurring somewhere over here, and B is going to be high, so B gives a 1 to Q instead of a 0 to Q. So doing this, you've got a historical copy of the last state of B, which is updated every time A has a rising edge, and that will always occur sometime during a rotation moment. So that might have some use, but what if you actually just want a circuit that will generate its own momentary pulse if you're going clockwise, and a different discrete pulse to show that you're going counterclockwise, and only when you're actually doing it. If a circuit's looking at this, it knows what you were last doing, but it doesn't know when. And if you try to monitor the clock for rising edges to see when did this actually happen, so you can trigger another circuit when you get a clock rising edge, well, you're kind of in a race condition, because at the moment that this is going high, you are going to be starting to clock B out to Q, and at the same time, you see this rising edge, and your other circuit says, oh, there's new data. But has this flip-flop had enough time to propagate B to Q? This might be going counterclockwise suddenly, so there's a logic 1 on its way through the flip-flop. Eventually the 1 makes it out as valid data, But in the meantime, while this was happening, you still have a 0. Somewhere around this point in time, your other circuit sees the clock and says, oh, let's check the data. It was 0 because you haven't updated yet. So you could try to do things like maybe take your clock and do sort of a time delay with a capacitor, resistor, filter. And then this is a delayed clock, so you can figure out how long it takes for data to propagate to Q. By the time this is stabilized at your most accurate current data, sometime after that, you generate your clock and your circuit can then look and see the valid 1. But this depends heavily on accuracy of this timing circuit, which can change component to component or change over temperature. Too much hassle with this, I think. There may be some applications where it's okay, but since we have guaranteed states here, as long as there's no contact bounce, we're just assuming an ideal rotation here and or debouncing going on. But we do have states that we can work with. So I want a circuit that's going to generate a clockwise pulse every time we go clockwise, or if we happen to be going counterclockwise, generate a counterclockwise pulse. That way I don't have to hack into the other signal, if we're going to call one a clock and one data, and then try to guess when data is valid with some other clever timing delays and stuff. This will just cleanly generate a guaranteed asserted signal when it has moved one way or the other. Somewhere after this process has started and before we're gone idle, because we're any second now we can get a new direction, within this timing of start to finish of the motion, somewhere in here we want to generate a signal on clockwise to tell us we have moved clockwise. So here, if I say at this point in time, if I'm looking at A, when A returns high again, I start generating my pulse, and by the time B has gone high, we're done with our movement, so we want to stop asserting our pulse and we're ready for a new movement as fast as it wants to come. We start moving again. When A is ready to go high, we start generating our pulse, and when B goes high and we're done moving, we're done generating our pulse. If this happened to have a counterclockwise movement somewhere in between here, then we would have generated a counterclockwise pulse as well. So I want to do sort of a state machine, or maybe it actually is a state machine, I'm not sure, but what I came up with is kind of an asynchronous mess. It's kind of like spaghetti logic, like using go-to statements in programming. It's all over the place, but I believe it does follow these states properly, so it's kind of like a stable state machine, but we'll see. I'm just calling it a state machine. So I've redrawn a reference waveform with A and B. So if A first goes low, and then B, and then A goes high, and then B goes back to high, that's clockwise. If our next movement occurs where B first goes low, then A goes low, then B goes high, and A goes high, that's counterclockwise. So I can use this reference waveform to design a circuit that'll generate a discrete clockwise and counterclockwise output pulse when we have moved clockwise or moved counterclockwise. The general approach I'm taking still uses a flip-flop, so I'm going to draw one flip-flop here for now. I'm basically going to pull the data to 5 volts, and then this is the edge-triggered clock, and I'm going to need to do some other gating here, but ultimately this is encoder A signal. So every time A has a rising edge, a 1 is going to propagate out to Q. I'm going to use reset because if I'm always going to clock a logic 1, there has to be a way to get a logic 0. So I'll be resetting, but I'm going to keep the set grounded because I'm not using it. I'm going to use the Q output to generate my clockwise pulse whenever we've had a clockwise rotation. And I'm basically going to need to do the same thing for the B encoder signal because I want to generate a counterclockwise pulse as well. So now this is going to start getting messy, but in order to reset this, let's say we have a power on initial condition where we have been reset. So Q is 0, Q bar is 1, and then first time we get motion, eventually both the A and the B are going to have a rising edge and we're going to get a clock of 1 out to Q. But it's going to stay 1, and every time we re-clock it with more motion, it's just going to clock 1. We need to reset it after we're done moving so that we are back to 0 on the Q output and waiting for the next rotation. So the goal is we start out low, we go high when we have detected motion, and we go low again. Same thing on here. We detect going counterclockwise, we go high temporarily, and then we go low. Reset is active high. So we need a place in our timing waveform where we can pick off some activity here and generate a signal going high, which will cause a reset. We start generating whichever direction we're supposed to, but we're doing it based on the rising edge of either one of these. And whichever one happens to start generating first, the other one is still going to have a rising edge as well. So as it is, we're going to get both clockwise and counterclockwise, one being slightly delayed from the other. So we need a way to cause a reset after this whole rotation, and we need a way to lock out whichever pulse we don't want. So trying to think of how do I go about causing a reset, and I only have these states here to deal with. When things go low, things go high, some are low. There's only so much to work with in this cycle, and I couldn't really think of a way to start generating this pulse and then say, okay, it's time to reset, and then come back out of reset. So I changed my thinking. Instead of having this thing running all the time, why don't I put it in sleep mode when I don't need any of this going on, and wake it up when we start rotating? Now it can be asynchronous and automatic. I don't need to tie anything to what's happening in here, really. I just need to be totally asleep and held in reset when this is idle and both lines are high. And by being in reset, Q on each one is 0. And that's my standby output. Clockwise, counterclockwise are both low because nothing's moving. Keep it in reset. I want it to be awake when stuff is happening. Stuff starts happening when A or B or both are low. That's when you're in the middle of a rotation. When they go high again, we're done. When A and B are high, I want a signal to be high because reset is active high. So that's an AND gate. So now when A and B are idle, they're both high. This is high. Both resets are high. When either of these fall, or both are low in the middle, this AND gate has a low and a high, or a high and a low, or a low and a low. The output will be low, so the resets are not activated and the chips are running. And we don't have to worry about setup and hold times and coming out of reset, really, because we come out of reset as soon as the first transition occurs. We are not starting to really clock anything in until the rising edge of what triggered this thing to come out of reset. So I haven't done the analysis, of course, but we are assuming that the time between the pulse going low and then going back high is going to be enough time for this to actually come out of reset and be ready to process. This is all just general. I didn't do deep analysis to make sure all these kind of conditions are met. We're just trying to come up with a concept, and if we need to do things to make it, say, manufacturable, then that's a different story, but this is just a concept. So we fixed one of the two problems, how to make this thing reset itself, because when it's in reset, we have started generating a pulse on whichever one. We go into reset when both of these go high again, and this will go low because the Q output is low. So that's how we end up generating a clockwise pulse that starts with our rising edge of our A, and it stops when both lines have gone high. But we still have the problem where we're actually going to get a rising edge clocking a 1 on both of these. It's just one's going to be first, the true one. So we need a way so that when something has triggered, we want to disable the other one for the rest of the cycle. That sounds like some sort of a lockout circuit or a gate to enable and disable the clocking of these. If we intercept the incoming A and B signal with an AND gate so that we can gate the whole process, the output of the AND gate will pass through if the other terminal is high. So we can do that for each one of these, but what do we tie it to? We can gate both of these at the same time with the same gate, because as long as we've triggered something, we just want to lock everything out really. We don't care until the cycle's done and we reset. So if we gate these with the same signal, what can we look at here in the process to tell us something has happened and it's time to lock everything else out, bring this gate low? When something has happened, it's the flip-flop outputs that change. Since we have an unused Q bar on each one, we might as well just tap into that and then leave this as a clean signal. In the case of clockwise, we'll say, we start out idle, Q is 0, Q bar is 1. And Q bar is also going to be 1 on this one when idle. When either one of these has been triggered, so a 1 has been clocked through, Q bar is going to become 0 on one of these, and that's when it's time to turn off this gate and not allow anything else to clock. So if we put an AND gate here, and we take the Q bar of each of these flip-flops, we take the output, bring it down, and use it as a gate enable sort of on these other input AND gates. When we're reset or sitting idle, Q bar is 1 and Q bar is 1. So the AND gate gives 1. And that actually enables both of these AND gates to pass through a 1 on B or a 1 on A. This AND gate has a 1, this AND gate has a 1. There's a 1 sitting at the clock inputs, but it's edge triggered, so it's not passing anything through yet. One of the two is going to go low first. Let's say it's clockwise, so A goes low, nothing has been triggered yet. B goes low, nothing has been triggered yet. But then the rising edge of A comes, so this goes high, the AND gate goes high, and the edge of the AND gate going high triggers a 1 to come out and start generating a clockwise pulse. A 1 on Q gives a Q bar of 0, so now we have a 0 and a 1, so this AND gate goes low, turns off the AND gate on each input, and now these can both change however they want. Nothing is going to trigger anymore. So we've already started generating our appropriate output. We've locked out the inputs. We've latched on one of these flip-flops, a 1. All we need now is to reset everything. And once this is done rotating and both go idle high, what we need to do is monitor the true input. So everything's kind of stuck. We're in the process of generating clockwise, but then both of these A and B return high because we're done rotating. So on this gate, we're directly monitoring ungated A and B. Both A and B are 1. We're holding the chip in reset. Q bar is 1 on each, so the gate output is 1. So the gate is open on A and B, waiting for the next rising edge to come and trigger a clock, lock out the other, generate the pulse, do a reset, and so on. So that's a bit of a mess because it evolved as I was going along, but that's the concept I came up with to look at a rotary encoder and interpret its two outputs to generate discrete controls. To implement the circuit, for the D flip-flops I'm using a 4013 which has 2 in it, and that's what I need. We have set, reset, data clock, and Q bar for 2 flip-flops. For the AND gates, I don't have any AND gates in my collection right now, which I'm going to have to order, but I do have lots of NAND gates, and when you take a NAND gate and throw an inverter on the output, you get an AND gate. I have lots of 4011 and 4049, so I'm going to use these together for each AND gate that I need. I'm going to try out the circuit now. I have the rotary encoder over here on the end, the logic circuit here, various decoupling capacitors and filters. I put one on a reset pin here because it was really noisy. I have 5 volts coming in here from a bench power supply, and all the inputs and outputs tapping into the Regal Scope's logic analyzer input. So the two A and B outputs are going into the circuit to be processed, as well as off to the logic analyzer, and then the output of the logic circuit is going to the logic analyzer. So I have 4 channels on the scope that are just logic analyzer, not analog input, coming to this header using the logic analyzer mode. There's this 16 channel input with nice DuPont friendly fly wires. So D0, 1, 2, 3, and then a ground are coming over to DuPont plugs and going to the circuit, so I can monitor what's happening going in and what's coming out. So this rotary encoder module takes 5 volts and ground, and it has onboard pull-up resistors, so I'm not using the switch. Clock and data are the 2 rotary encoder outputs that are pulled high and go active low when in rotation. So on the logic analyzer, D0, 1, 2, and 3, D0 is rotary encoder signal A, then we have signal B, so those are going into the logic circuit, and then coming out we have my generated clockwise signal and my generated counterclockwise signal. So the flat edge of the encoder knob is over here on the left. I'm going to rotate clockwise several times and just see what happens. So 1 rotation clockwise, and we can see that A went low and then B went low after, and we get a clockwise pulse. So I'll try multiple clockwise rotations. Okay, so I captured 2, and there was another one in progress off screen. I'll try again and again. Maybe I'll change the time division. Try to capture more. Clockwise, clockwise, there's a whole bunch. So since these are both low and then they go high, this was the trail end of 1 rotation, and it gave a clockwise pulse. Then I did several more rotations and got several more clockwise pulses only, and then it was in the middle of another one and it's off screen. So now if I go counterclockwise, just a single one, well, I accidentally did 2. So now clockwise out is quiet, but I'm getting a counterclockwise pulse, and output B from the encoder is what went low first and then A. I'll do more counterclockwise turns. There's another one, and I went slower, so it took longer to complete the rotation on A and B. I'll try several, and there's 4 hits that all registered properly counterclockwise. I zoomed in, so I'm going to try capturing 1 clockwise rotation and see if we can analyze it. So, going clockwise, A went low first, then B went low, and then as the disk was rotated, eventually A was released and went pulling high, and then B was released pulling high, and we get a clockwise output. So we can see the output pulse is being generated in the time between one of the inputs returning to high and the other input returning to high. That's how wide the trigger output pulse is. Using hardware instead of software to decipher a rotary encoder and make useful signals that we can detect the direction and do something purposeful with it.